Hello everyone. My name is Yermakov. I am from Karazin National University. I plan to talk about metasurface for near field light control and coupling of light, but I will then focus on the nanostructures for coupling of light into fibers. So optical fiber is the main carrier of optical signal. It consists of glass inside the glass. The core is the doped glass, and around it is the cladding, also glass. And it allows to conduct the signals for hundreds of kilometers with minimum losses due to the total internal reflection phenomenon. And this is a map of subsea optical fibers, telecommunications. So the main carrier of our information are optical fibers, not radio, not GPS, not antennas, but exactly the optical fibers. This is just carried of the map of subsea fibers. But also they're widely used in different applications, in detectors and sensors, for space technology, for car technology, and of course in medicine. For instance, in endoscopy and laparoscopy. In all applications, well, you have a small hole and you need to detect something or to observe something behind this hole. But there is such a fundamental problem connected with fibers. We call it the fiber coupling efficiency. Simple words, this is the efficiency of the transformation of plane waves incident at the end phase of fiber into the guided modes of the fiber. And under the normal incidence, this coupling efficiency is almost ideal, but it rapidly drops with oblique incidence. It decreases so quickly, then at the angle around 15-20 degrees, the real values are too small for practical applications. This is a problem, of course. It significantly limits all these applications, the detectors, spectroscopy, endoscopy, medicine, sensors, etc. And to overcome this problem, we follow the Laban fiber concept, which assumes the merging of nanostructures with fiber. They could be inside the fiber, around the fiber, and on the fiber tip. So we focus exactly on the fiber tip nanostructure. And of course, we are not the first who proposed this idea. Here you can see one of the most successful application, one of the most successful example before us, where the authors put the periodic array of gold nanodiscs at the fiber tip. And here are the main result. So the orange dots corresponds to the fiber coupling efficiency without nanostructure, and blue dots to the fiber tip with gold nanodiscs. Here we have the logarithmic scale. And one can see the great coupling efficiency enhancement, but at the same time, the practical values are still very low. 10 to minus 4, 10 to minus 5, and at large angles, even 10 to minus 6. This is not enough for practical applications. So first of all, we state our main challenge as to achieve big coupling efficiency, maybe percent level of coupling efficiency for large angles, where this is the most difficult case. Here I propose the following structure consisting of such an axial symmetric structure from silicon nitride. It represents a periodic array of concentric rings, and it acts as an axial symmetric diffraction grating, where the first diffraction order coincides with the fiber axis. So this is the idea. But at the same time, due to the axial symmetry, we obtain the independence of the azimuthal angle. So the light can come from different sides, from right or from left. It doesn't matter, only the angle of incidence matters. And also, due to the axial symmetry, we have almost full independence on the polarization. which is also important for practical applications. Here I skip the analytical model and numerical model and come to the fabrication and the main results. My colleagues from Germany, from Leibniz Institute of Photonic Technology, have produced these nanostructures, the Fiber-optic, with such a multi-step, difficult procedure, including electron beam lithography, ion beam etching, with following resist removal. But finally, they obtained this the following structures. So here you can see several single mode fibers. The central one is unstructured, while we have the different number of rings at different ones. And this is the central result of this work, where we see the experimental data and numerical simulation of in-coupling efficiency for T and TM polarizations. This dashed gray line corresponds to the bar fiber without nanostructure, and color lines correspond to the optical fiber with different number of rings at the fiber T. So one can easily see the great enhancement of in-coupling efficiency for the angles larger than 60 degrees. I think to summarize this work, one can just remember this figure where we show that we demonstrate the enhancement of fiber efficiency by several orders of magnitude with this concentric rings nanostructure. This work was published in ICAP Photonics and got the front cover of this journal. And a bit later, it was has been chosen among the top 30 most important and exciting optics and photonics research in 2021, according to Optics and Photonics News Journal. But then we go further. We improved our analytical and technological procedures, especially my colleagues made it possible to use direct laser writing or three-dimensional nanoprinting using the photopolymerization process, which allows to produce such type of structure very quickly, quite cheap, very precise. And in the previous case, the structure was fabricated during 2 months. Here, it can be done during 30 minutes, so it's very fast. But also here we can change the height, the width of each ring, and even the distance between any two rings from this array. It gives us additional degree of freedom and additional improvement. But here we can do it only with the polymer with quite small refractive index, 1.55 by the refractive index of the core. It's just less than 1/10 smaller. So first of all, we have checked that it works with polymer, and it's so. So here, solid lines, this is experimental data. Dashed lines, this is simulation data. And we propose several nanostructures with different maximum in angular spectra. So we open the diffraction channel at different angles, and we can see that the experimental and simulation data fit quite well, and it works with polymer. So then we improve the structures. First of all, we take double pitch gratings where we open 2 diffraction maxima at 25 and at 60 degrees. Such a ring structure consists of 2 types of rings. And even more advanced case is we use so-called aperiodic nanostructure, where each ring is different, it differs from each other, and it gives us near flat angular dependence. So in simple words, it means that we have almost approximately the same coupling efficiency at any angle of incidence, and it is quite high. Then we compare different designs. I propose to look only at the bottom figure. These color regions correspond to the angular ranges where we achieve the necessary level of coupling efficiency. So for the case without nanostructure, it's about 10 degrees, but for the cases shown at the last slide, these 2 cases cover almost whole angular range. And this work was also recently published just at the beginning of this year in the Applied Physics Reviews Journal. I would like to thank my colleagues, Professor Marcus Schmidt from Leibniz Institute of Photonic Technology in Vienna, Germany. All fabrication and experimental parts have been done in this university, in his group. And also Professor Yuri Kishar from Australian National University for giving this idea. So Marcus presents the fiber optics community, nanophotonics community, and merging the ideas, we come to these beautiful results. Finally, I would like to remind that the war is still going. I'm from Kharkiv, and that's how the city center looks. About 1 year ago, it's my university, especially this is the lecture room where I have studied. It's my home. I request to pay attention to this problem, despite we are all tired from this. Thank you for your attention.